Ketones and aldehydes exist as a mixture of constitutional isomers. The keto isomer and the enol isomer. The term enol is used because it describes an alkene with an alcohol hydroxyl directly attached. In other words, an alkene alcohol. Here's a representation of a keto isomer and its related isomeric enol. We can see that in this equilibrium, the double bond changes its position from between the carbon and oxygen to between the carbon and carbon. And the hydrogen on the alpha carbon changes its position to become attached to the oxygen. This equilibrium can occur under acid or base conditions. These are a special type of constitutional isomer that are called tautomers. Tautomers are constitutional isomers that can chemically interconvert. As pointed out in this equilibrium, that interconversion can occur either in the presence of base or acid. This interconversion is called keto to enol tautomerization, and it is an equilibrium reaction that occurs spontaneously in both acid and base conditions. It is almost impossible to get purely one tautomer by itself. We're now going to look at the mechanism by which this equilibrium occurs. First, in base, we start with the ketone, and the base deprotonates the alpha carbon. Remember that this alpha carbon in a ketone or aldehyde is generally more acidic than a typical CH bond. This creates an enolate, and as we discussed in the previous chapter, the enolate has a resonance structure. When we have multiple resonance structures, we can imagine either resonance structure reacting. In this case, the original resonance structure would react in the reverse reaction by grabbing a hydrogen off of an acid and becoming reprotonated on the alpha carbon. That would just recreate the original ketone or aldehyde. In contrast, the other resonance structure can react by becoming protonated, acting as a base, removing a hydrogen from an acid, and becoming protonated on the oxygen. That creates the OH, and it leaves the double bond in its resonance shifted location. The acid catalyzed mechanism involves first the ketone or aldehyde reacting as a base, removing a hydrogen from the acid, in other words, becoming protonated on the carbonyl oxygen. We can then draw a resonance structure where the carbon-oxygen double bond has moved out onto the oxygen, leaving effectively a carbocation on the carbon. We've seen in the E1 reaction that when we have a carbocation, we can deprotonate a carbon adjacent to that. So a base would come over, remove a hydrogen from the adjacent carbon, and the pair of electrons from the CH bond would move down, forming a double bond. Either of these mechanisms are possible. It just depends on the pH of the system in which the keto or enol form is dissolved. In most cases, isolated ketones and aldehydes prefer to exist as the keto tautomer. In other words, the equilibrium favors the keto structure. Here are two examples. In acetone, we can see that the keto structure is greater than 99% and the enol is less than 1% at equilibrium. And similarly, in cyclohexanone, the keto structure is greater than 99% and the enol structure is less than 1%. However, there is a circumstance in which the enol isomer can be present in a larger amount at equilibrium. This occurs in systems where there are other functional groups nearby that can hydrogen bond with the OH in the enol form. Here's an example where we have two ketones related beta to each other. If one of the ketones becomes the enol, the hydrogen can reach across the molecule and hydrogen bond with the other ketone oxygen. This is favorable because if we look, this essentially forms a pseudo six-membered ring. And we know that six-membered rings have no ring strain. In this case, then, we can have as much as 25% of the enol form of this ketone present.